This is part of a series I call the Making Evidence-Based Medicine Simple series, or MESS for short. In this MESS Mini, we will review how to assess the heterogeneity of study results in a meta-analysis with forest plots and heterogeneity statistics. These are the questions we need to answer as we review the results of a meta-analysis. Were the results similar from study to study? What are the results of the meta-analysis? And how precise were the results? The first results question is, were the results similar from study to study? I've underlined the word results. This is to emphasize that the question above is asking about statistical heterogeneity of the study results and not clinical heterogeneity of study design. One of the fundamental assumptions required to combine individual study results in a meta-analysis is that the results of the individual studies are essentially the same or homogeneous. Heterogeneity can be defined as a difference between study results that is beyond what is due to random error. Small differences between study results are assumed to be due to random error. If the results of the individual studies vary greatly, are heterogeneous, then combining the studies into a meta-analysis may be invalid. There are several ways to test for heterogeneity of study results. We will look at graphing the study data with forest plots and both qualitative and quantitative statistical tests of heterogeneity. Forest plots vary, but in general include the sections in the illustration above. This includes a section for data about the individual studies, a section for meta-analysis summary statistics, the heterogeneity statistics, and the forest plot itself. We'll take a closer look at each of these. This is the individual study data section. In the first column, there are 16 studies included in the meta-analysis that are listed alphabetically by the author's last name. The second column includes the number of events and total number of patients in each of the study groups. The third column includes the study weight. This is a measure of how much an individual study influences the meta-analysis summary statistic. Studies with a higher weight are those with a larger sample size and smaller confidence interval. The study weight can also be illustrated by the individual box size in the plot. The study by Pinckney et al. Had the greatest weight at 14%. The last column includes the individual study statistics. In this case, it is a risk ratio with the 95% confidence interval. Not all meta-analyses include all four of these elements, but columns 1 and 2 are commonly included. The summary statistics section includes the answer to the meta-analysis results questions. What were the overall results of the review, and how precise were the results? The data includes the total number of events, 263, and the total number of patients, 1,846 in the intervention group, and the total number of events, 388, and the total number of patients, 1,849 in the control group. In addition, the total weight of the individual studies should add to 100%. The meta-analysis summary statistic is a risk ratio of 0.65 and confidence interval of 0.51 to 0.83. This can be interpreted as the risk of the outcome in the intervention group is 0.65 times the risk of the outcome in the control group. Since this is a ratio, a risk ratio of 1 would indicate no difference. The 95% confidence interval does not include 1, so that the difference is statistically significant. You can be 95% confident that the true summary statistic falls between 0.51 and 0.83. The last question, how precise are the results, refer to the width of the confidence interval around the summary statistic. The narrower the confidence interval, the more precise the results. This is a forest plot. It enables us to graphically assess for heterogeneity of study results, as well as to determine the meta-analysis summary statistics and its precision. The x-axis represents the summary statistic, in this example, a risk ratio. The y-axis represents the summary statistic of no difference. Notice that the y-axis is centered on 1. This should be true of any summary statistic based on a ratio. A risk ratio, relative risk, or odds ratio equal to 1 indicates no difference. Or alternatively, the risk or odds in the intervention and control group are equal. A risk ratio less than 1 favors the intervention group, and a risk ratio greater than 1 favors the control group. If the summary statistic had been a risk difference, median difference, or mean difference, the y-axis would have been centered on 0, the point of no difference. The boxes and lines indicate the results of individual studies. The box that is centered on line indicates the individual study statistic, in this case the risk ratio. The relative size of the box indicates the study weight. This indicates how much the individual study influences the summary statistic. This is related to the study size and the width of the confidence interval. It was also expressed as a percentage in the individual study section data. The line through the box indicates the confidence interval. The larger the sample size, the narrower the confidence interval. The two studies whose confidence interval ends in arrows indicate that the confidence intervals extend beyond the range of the x-axis. Confidence intervals that cross the y-axis indicate the individual study statistic was not statistically significant. 5 of the 16 studies have a difference that is statistically significant. That is, the confidence interval did not include 1. The diamond shape represents the meta-analysis summary statistic. Notice that it is narrower than any of the individual studies. One of the benefits of the meta-analysis is that adding individual studies results in a larger sample size. That larger sample size results in a narrower confidence interval. Narrower confidence intervals indicate a greater precision. In this example, the diamond corresponds to a risk ratio less than 1 favoring the intervention. The width of the diamond does not cross the line of no difference, the y-axis, indicating that the summary statistic risk ratio is statistically significant. There are 3 things we can look at on a forest plot to determine if the study's results are homogeneous. We can look at the clustering of the individual study's point estimates, in this study the risk ratios, to determine if they are similar in magnitude. We can also look to see if the study results all favor the same direction of effect, whether favoring the intervention, favoring the control, or if there is no difference between the intervention and the control. Finally, we can see if the study's confidence intervals overlap. If the confidence intervals overlap, then the difference in the point estimates are likely due to chance or random error, and the results are homogeneous. However, care should be taken in interpretation of forest plots for heterogeneity, which include many individual studies with a small sample size, as their confidence intervals are likely to be wider and more likely to overlap. In this plot, the study point estimates seem to be relatively similar in magnitude. In addition, all but 2 of the point estimates favor the intervention, and the 2 that do not are very close to the ones that do. Finally, a line can be drawn that intersects the confidence intervals. I would conclude that the study results are homogeneous and not heterogeneous. What happens if a new study indicated in red is published and you wish to add it to the meta-analysis? The new study point estimate is very different from the other studies. The new study favors the control, while most of the others favor the intervention group. In addition, you cannot draw a line that intersects the confidence intervals of the individual studies. I would conclude that the study results are heterogeneous and not homogeneous. So what do we do with the new study if there is significant heterogeneity? We need to review the study closely and review the definitions of the population, interventions, controls, and outcomes, and study methods to determine if the difference in statistical heterogeneity may be due to clinical heterogeneity. For example, if I look closer at the new study and it reveals that it only included patients who are at higher risk of the outcome, for example, the new study included only patients with perforated appendicitis, while the other studies included only patients with non-perforated appendicitis, then it may be possible to exclude it. Alternatively, you can conduct a sensitivity analysis. A sensitivity analysis determines the meta-analysis summary statistic with and without the new study to determine the study's impact on the summary statistic. Sometimes it may not be possible to combine the study results due to heterogeneity, and the study is completed as a qualitative systematic review rather than a quantitative meta-analysis. Unfortunately, there are no guidelines on when to abandon a meta-analysis due to heterogeneity, so it's left to the author's discretion. In addition to visual inspection of forest plots, there are qualitative and quantitative statistical tests of heterogeneity. The Cochrane Q is the most commonly used qualitative test and is based on the chi-squared test. The Cochrane Q is a statistical test of association. It yields a p-value indicating yes, there is heterogeneity, a p-value less than 0.1, or no, the study results are not heterogeneous, a p-value greater than 0.1. Unfortunately, the Cochrane Q can yield both false positive and false negative results under certain conditions. Due to these problems, a quantitative test is often used. The most common test is the I² test. The I² test presents a numeric magnitude of association. The interpretation of the I² test is 0 to 40% might not be important, 30 to 60% represents moderate heterogeneity, 50 to 90% represents substantial heterogeneity, and 75 to 100% represents considerable heterogeneity. Unfortunately, there is no agreed upon cutoff of I² for which a meta-analysis should not be conducted. I've expanded the meta-analysis heterogeneity statistics from the table. The chi-squared statistic is 30.95 with 15 degrees of freedom, 16 studies minus 1. The p-value of less than 0.1 indicates that the individual study results are statistically significantly different from homogeneous. In other words, the study results are heterogeneous. The I² of 52% indicate moderate or substantial heterogeneity by the Cochrane definitions. Forest plots and heterogeneity statistics help to determine if it's appropriate to combine individual studies into a meta-analysis. Once the decision is made to combine the results, there are multiple methods that can be used. You will see the terms fixed effects model and random effects model attached to the summary statistics of most meta-analyses. These indicate the statistical approach that were used to combine the data. This forest plot indicates that a random effects model was used. There are a variety of statistical methods using both the fixed effects and random effects models that generally yield similar results. The fixed effects models assumes a single true value and generates narrower confidence intervals with greater precision. The random effects model is most used. The random effects model assumes a random sample of studies and puts more weight on smaller studies than is seen with the fixed effect models. The random effects model generates a more conservative estimate of precision in the form of a wider confidence interval, but is more susceptible to publication bias. There is considerable debate among statisticians over which approach should be used and under what conditions. It appears to be a trade-off between the fixed effects model, which is stable and robust, but based on an unlikely assumption, and the random effects model, which is less stable and sometimes unpredictable, but based on a more likely assumption. This is an example of another use of forest plots from a clinical trial of therapeutic hypothermia on cardiac arrest outcomes in adults. This is a subgroup analysis. The categories of the subgroup are assessed for the impact on the study's primary outcome. The outcome in all patients is included in the top row. Which subgroups to include should be predetermined based on the plausible association with the study outcome. In this study, the subgroups include sex, age, time of return of spontaneous circulation, initial rhythm, and shock on admission. The confidence intervals for the relative risk for all subgroups cross the y-axis of no difference at a relative risk of 1. Additionally, the confidence intervals for the relative risk for all subgroups cross 1. There was no statistically significant difference in the study outcome by any of the subgroups. Notice that this does not directly compare one subgroup category to another. For example, this does not compare male and female categories of the subgroup sex with the outcome to each other. In summary, homogeneity should be assessed prior to combining the individual study's results in a meta-analysis. Homogeneity can be assessed graphically using forest plots, with qualitative statistical tests such as the Cochrane Chi² and with quantitative tests like the I². Whether to use a fixed or random effects model to combine the data is a matter of debate, and a decision should be made based on the degree of heterogeneity. Finally, forest plots can be used to assess the influence of subgroups on the outcomes of a clinical trial.